Since 2016, NASA's Juno spacecraft has been peering beneath Jupiter's beautiful but deceptive cloud layers, uncovering secrets that challenge everything we thought we knew about the solar system's largest planet. What mission scientists discovered deep within Jupiter's atmosphere defies explanation. A mysterious central storm system unlike anything found elsewhere in the universe. The data streaming back from Juno's sensors reveals that Jupiter isn't just a giant ball of gas, but a world harboring terrifying forces and unexplained phenomena that could reshape our understanding of planetary formation itself. The mysterious central storm discovery. Deep within Jupiter's core lies a discovery that has left planetary scientists speechless. Juno's microwave radiometer penetrated 350 kilometers below the cloud tops and detected what appears to be a permanent central vortex spanning thousands of kilometers across. Unlike the Great Red Spot or other visible storms, this deep atmospheric feature shows no signs of the typical cyclonic rotation patterns found elsewhere on Jupiter. Dr. Scott Bolton, Juno's principal investigator, describes it as a hurricane frozen in time, a massive atmospheric disturbance that appears to have remained unchanged for potentially millions of years. The storm system generates electromagnetic pulses that interfere with Juno's instruments, creating data gaps that suggest something far more complex than simple atmospheric circulation. Most disturbing is the storm's perfect geometric structure. It forms concentric rings with mathematical precision that defies known meteorological processes. The central vortex appears to extend all the way down to Jupiter's metallic hydrogen core, creating a direct channel between the planet's surface storms and its deepest interior regions. The beginning of the mission. Juno launched on August 5, 2011, beginning a 5-year journey to reach Jupiter and unlock the secrets of the solar system's formation. The spacecraft was designed with a unique polar orbit that would allow it to study Jupiter's interior structure without being destroyed by the planet's deadly radiation belts. Lockheed Martin built the titanium-armored probe to withstand radiation levels 1,000 times stronger than those that would kill a human instantly. The mission's primary goals included mapping Jupiter's gravitational field, studying its atmospheric composition, and determining whether the planet has a solid core. NASA scientists equipped Juno with 9 sophisticated instruments, including a JunoCam for public outreach and scientific imaging. The spacecraft's 3 massive solar panels make it the most distant solar-powered probe ever launched, generating electricity from sunlight 25 times weaker than that reaching Earth. After traveling 2.8 billion kilometers, Juno successfully entered Jupiter's orbit on July 4, 2016, beginning what would become one of the most revolutionary planetary exploration missions in history. Jupiter is the world of chaos. Jupiter's atmosphere operates on a scale of violence that dwarfs anything found on Earth. Wind speeds reach 640 kilometers per hour, nearly twice as fast as the strongest hurricanes ever recorded on our planet. The atmospheric bands that give Jupiter its distinctive striped appearance are actually jet streams containing more energy than all of Earth's weather systems combined. Dr. Andy Ingersoll from Caltech discovered that Jupiter's storms can maintain their intensity for centuries, with some features persisting longer than human civilization has existed. The planet's rapid 9.9-hour rotation creates Coriolis forces so powerful they tear apart smaller storm systems while strengthening larger ones. Temperature variations between different atmospheric layers create vertical wind shears that would instantly destroy any Earth-based aircraft. Most shocking is the discovery of thermal towers, massive columns of superheated gas that erupt from deep within Jupiter's interior, carrying energy equivalent to multiple nuclear explosions every second. These thermal plumes create the pop-up clouds that appear suddenly at atmospheric boundaries, representing eruptions of material from depths of over 100 kilometers below the visible cloud deck.
Io, the volcanic moon.
Io, Jupiter's innermost large moon, represents a world that's literally being torn apart by gravitational forces. This sulfur-covered hellscape hosts over 400 active volcanoes, making it, well, the most geologically active body in the solar system. Dr. Rosalie Lopez from JPL has cataloged volcanic eruptions on Io that blast material 500 kilometers into space. That's high enough to reach from Earth's surface all the way up to the International Space Station. Jupiter's immense gravity, along with the gravitational tugging from Europa and Ganymede, creates tidal flexing that generates enough internal heat to actually melt Io's rocky interior. The moon's volcanic activity pumps 1 ton of material per second into Jupiter's magnetosphere, creating a plasma torus that, feeds the planet's radiation belts. Some of Io's volcanic plumes reach temperatures of 1,800 degrees Celsius, that's hot enough to melt copper, while ejecting sulfur dioxide snow that gives the moon its distinctive yellow and orange appearance. Juno's observations reveal that Io's volcanic activity directly influences Jupiter's auroras, creating an electrical connection between the moon and the planet that generates 5 million amperes of current flowing through space. Research on Jupiter's magnetic field. Jupiter's magnetic field represents one of the most powerful and complex magnetic environments in the solar system. Generated by electrical currents in the planet's metallic hydrogen core, the field extends over 1 million kilometers from Jupiter's surface, so large it would appear 5 times the size of the full moon if you could actually see it from Earth. Dr. Jack Connerny from NASA Goddard leads research showing that Jupiter's magnetosphere contains enough energy to power human civilization for millions of years. The magnetic field traps charged particles from the solar wind, creating radiation belts that are 10,000 times more intense than Earth's Van Allen belts. Most mysteriously, Juno discovered that Jupiter's magnetic field has an asymmetric structure with a distinct northern magnetic anomaly, a feature that really shouldn't exist according to traditional magnetic field models. The field appears to be generated by shallow flows in the metallic hydrogen layer, rather than by deep convection processes as previously assumed. This discovery suggests that Jupiter's interior structure is far more complex than simple models predict, with multiple layers of conducting fluids creating a dynamo system unlike any other planet we've studied. Juno mission peaks under Jupiter's surface. Juno's gravitational measurements have, honestly, revolutionized our understanding of Jupiter's internal structure by revealing what actually lies beneath those swirling clouds. The spacecraft's precision tracking detected gravitational anomalies indicating that Jupiter has a fuzzy or dilute core, rather than the distinct, solid center that scientists had expected. Dr. Tristan Guillot from Observatoire de la Côte d'Azur analyzed the data, showing that heavy elements are mixed throughout Jupiter's interior instead of being concentrated in a central core. This partially dissolved core extends outward for thousands of kilometers, containing between 7 and 25 Earth masses of rocky material distributed through the planet's metallic hydrogen region. The discovery suggests that Jupiter suffered a massive collision early in its formation, an impact so violent it scattered core material throughout the planet's interior. Microwave soundings reveal that Jupiter's ammonia concentration varies dramatically with depth, creating distinct atmospheric layers that trap and release gases in complex cycles. The planet's interior rotates as a solid body down to depths of 3,000 kilometers, below which differential rotation creates shearing forces that generate the observed magnetic field patterns. Jupiter's formation and composition. Jupiter's formation story has been, completely rewritten by Juno's discoveries about the planet's water content and internal structure. Dr. Chung Lee from UC Berkeley found that Jupiter actually contains about 3 times more water than expected, with concentrations that, interestingly, vary dramatically between different atmospheric regions. The uneven water distribution suggests that Jupiter formed through core accretion rather than gravitational collapse, meaning it slowly built up from solid materials before capturing gas from the solar nebula. Heavy elements make up between 3 and 9% of Jupiter's total mass, far more than previous models predicted, which indicates the planet accumulated significant amounts of rocky planetesimals during its formation. The discovery of phosphine gas in Jupiter's upper atmosphere provides evidence of vertical mixing, which transports material from deep interior regions where the gas forms under extreme pressure. Isotopic ratios measured by Juno even suggest that Jupiter migrated inward toward the Sun during its early history before moving back to its current position, a grand tack model that helps explain the architecture of our entire solar system. This migration scattered asteroid belt material and prevented super-Earth formation in the inner solar system. Jupiter as Earth's protector. So, Jupiter actually serves as Earth's gravitational guardian, deflecting potentially catastrophic asteroids and comets away from the inner solar system. According to computer simulations by Dr. Kevin Grazier, without Jupiter's immense gravity, Earth would be bombarded by impacts 1,000 times more frequently, making complex life, virtually impossible. The planet's orbital resonances, create asteroid families and gaps in the asteroid belt, which prevents small rocky bodies from spiraling toward Earth. During the early solar system, Jupiter's migration scattered icy comets from the Kuiper belt, and many of those actually delivered the water that fills Earth's oceans today. The planet also captures interstellar objects entering our solar system, like asteroids from other star systems that could otherwise pose unpredictable threats to Earth. Recent studies show that Jupiter's gravitational influence extends beyond Neptune's orbit, affecting the trajectories of long-period comets that originate in the Oort cloud. But here's the thing. Jupiter occasionally sends objects toward Earth as well, since its gravity can perturb comet orbits and redirect them into the inner solar system. So, this double-edged protection means Jupiter both shields and sometimes threatens Earth, maintaining a delicate balance that has allowed life to flourish on our planet.
The Great Red Spot Mystery.
The Great Red Spot has been shrinking for over 150 years, and Juno's close-up observations are finally revealing why this iconic storm may be slowly dying. Dr. Amy Simon from NASA Goddard discovered that the storm has lost 50% of its width since the 1800s, and it continues shrinking at an accelerating rate. Juno's infrared spectrometer found that the Great Red Spot extends about 300 kilometers deep into Jupiter's atmosphere, much deeper than any hurricane on Earth, but actually shallower than expected for such a long-lived feature. The storm's distinctive red color comes from complex organic compounds created when ammonia and hydrogen sulfide are exposed to ultraviolet radiation from the sun. Wind measurements show that the storm's outer edges rotate faster than its center, creating shearing forces that may be gradually tearing the vortex apart. Most mysteriously, the Great Red Spot sometimes changes color from deep red to pale orange, which suggests chemical reactions are happening within the storm system. Computer models suggest the storm may completely disappear within the next 50 years, ending a 300-year-old atmospheric feature that has served as Jupiter's most recognizable landmark.
The Atmospheric Rivers Discovery.
Juno's microwave radiometer uncovered a previously unknown feature that might be Jupiter's most important atmospheric discovery: massive atmospheric rivers flowing beneath the visible cloud layers. These invisible currents transport ammonia and water vapor across thousands of kilometers, working like conveyor belts that redistribute heat and chemicals throughout Jupiter's atmosphere. Dr. Karen Dewar from the Weizmann Institute identified these deep atmospheric streams using radio emissions that can penetrate Jupiter's thick clouds. The atmospheric rivers flow at depths of 100 to 200 kilometers below the surface, carrying 10 times more material than all of Earth's atmospheric circulation combined. These hidden currents help explain how Jupiter's bands maintain their distinct chemical compositions, even with all the planet's turbulent mixing. The rivers seem to connect polar cyclones with equatorial jet streams, creating a global circulation pattern that operates independently of surface weather. Most remarkably, these deep atmospheric flows may be directly connected to Jupiter's metallic hydrogen core, suggesting that the planet's weather systems extend all the way to its center. This discovery really shows that Jupiter's atmosphere is a three-dimensional system, way more complex than the simple layered structure scientists used to assume. Juno's revelations about Jupiter have, honestly, shattered our understanding of the solar system's giant. From mysterious central storms to atmospheric rivers flowing beneath the clouds, Jupiter harbors secrets that challenge fundamental theories about planetary formation. The discovery that our cosmic protector contains a partially dissolved core and complex interior dynamics proves there's still so much to learn about our celestial neighborhood. So, which Jupiter mystery fascinated you the most? Share your thoughts below. If you enjoyed uncovering these incredible planetary secrets, go ahead and hit that like button, share with fellow space enthusiasts, and subscribe to Future Facts for more mind-blowing cosmic discoveries.
Join us as we delve into the mysterious journey of interstellar visitors captured by modern astronomy, including the enigmatic Oumuamua and the recently discovered 3I/Atlas. This exploration combines scientific discoveries with eyewitness accounts and expert analyses to unravel the secrets of these cosmic wanderers. From Navy pilot encounters to Harvard theories about alien technology, prepare for revelations that challenge everything we know about our place in the universe. Oumuamua discovery and anomalies. Discovered in October 2017 by the Pan-STARRS survey in Hawaii, Oumuamua became the first confirmed interstellar object detected passing through our solar system. Its bizarre elongated shape, estimated at 800 meters long and 80 meters wide, resembled nothing astronomers had ever seen before. Most puzzling was its unexplained acceleration away from the Sun without any visible cometary tail or outgassing that typically causes such behavior. Harvard's Avi Loeb controversially suggested it might be an artificial light sail created by extraterrestrial intelligence, while other scientists proposed it was a natural asteroid or exotic hydrogen iceberg. The object's extreme 10:1 length ratio defied conventional understanding of how cosmic bodies form and maintain structural integrity across interstellar distances. Despite intensive observations from multiple telescopes including Hubble and Spitzer, Oumuamua's exact nature remains hotly debated. Its discovery ignited an entirely new field of astronomy focused on studying interstellar visitors, fundamentally changing how we view our cosmic neighborhood. The mystery deepened when the object's trajectory showed it had been traveling through space for hundreds of millions of years before reaching us. UFO-UAP encounters and theories. In recent years, U.S. Navy pilots have reported encounters with unexplained aerial phenomena that defy conventional physics. The most famous incident occurred in 2004 off California's coast when Fravor encountered the now legendary Tic Tac UFO. He described a white, smooth craft roughly 40 feet long that exhibited extraordinary agility, instantly accelerating from 0 to hypersonic speeds without visible propulsion. The object demonstrated capabilities that seemed to violate known aerodynamic principles, including right-angle turns at extreme velocities and the ability to disappear and reappear miles away within seconds. Some researchers have theorized these phenomena might involve plasma projection technology or advanced stealth systems using electromagnetic field manipulation. Government officials have confirmed the retrieval of multiple crashed unidentified objects, with sources claiming over 10 such recoveries in U.S. possession alone. These revelations have prompted increased congressional scrutiny and calls for transparency from intelligence agencies. The correlation between these sightings and interstellar object discoveries has led some experts to speculate about potential connections between extraterrestrial monitoring and our detection of visitors like Oumuamua. Bob Lazar analysis. Bob Lazar brought widespread attention to claims of reverse-engineered extraterrestrial technology allegedly housed at the classified Area 51 facility in Nevada. Beginning in the late 1980s, Lazar detailed supposed anti-gravity propulsion systems powered by element 115, a super-heavy element that was purely theoretical at the time of his claims. He described witnessing 9 alien craft with propulsion systems that manipulated gravity waves through element 115's unique properties when bombarded with protons. While many scientists remained skeptical due to Lazar's inability to provide verifiable credentials and inconsistencies in his educational background, element 115 was eventually synthesized in laboratories in 2003, lending some credibility to his technical descriptions. Government investigators found discrepancies in his claimed security clearances, though supporters argue this could indicate compartmentalized programs beyond standard classification levels. Some aspects of Lazar's descriptions of field propulsion and spacetime manipulation have gained renewed interest as theoretical physics advances in areas like the Alcubierre warp drive concept. His influence on UFO culture remains significant despite ongoing scientific skepticism about the feasibility of the technologies he described. Light sail hypothesis. Harvard astrophysicist Avi Loeb proposed the revolutionary hypothesis that Oumuamua represents not a natural celestial body but an artificial light sail, an ultra-thin spacecraft propelled by stellar radiation pressure. This theory elegantly explains the object's puzzling non-gravitational acceleration without visible outgassing, as photons from the Sun could provide sufficient thrust on an extremely thin, reflective surface. Loeb calculated that for radiation pressure to account for the observed acceleration, Oumuamua would need to be less than a millimeter thick while maintaining its football field length. Though highly controversial within the scientific community, Loeb's hypothesis has forced astronomers to seriously reconsider the possibility of detecting engineered objects traversing interstellar space. His work has accelerated interest in the search for extraterrestrial intelligence, SETI, and emphasized the need for more sophisticated detection and analysis methods for future interstellar visitors. Critics argue that natural explanations involving exotic ices remain more plausible, but Loeb maintains that extraordinary claims require extraordinary investigation. His advocacy for considering artificial origins has sparked heated debates about scientific methodology and the search for extraterrestrial technology in astronomical observations. 3I Atlas, the new discovery. The third confirmed interstellar visitor, 3I Atlas, was discovered in early 2025 by the Asteroid Terrestrial Impact Last Alert System, marking another milestone in interstellar astronomy. Preliminary observations suggest this massive object measures between 10 and 20 kilometers in diameter, making it potentially 50 to 200 times larger than Oumuamua and representing a statistical anomaly that challenges our understanding of interstellar object populations. Moving at speeds exceeding 60 kilometers per second relative to our solar system, 3I Atlas displays unusual brightness characteristics and possible metallic surface composition detected through spectroscopic analysis. NASA's James Webb Space Telescope has captured infrared signatures suggesting engineered materials inconsistent with natural asteroid or comet formation. The object's trajectory and timing of arrival have raised eyebrows among researchers, with some noting its approach coincides with humanity's increasing technological capabilities and space exploration activities. Unlike previous interstellar visitors, 3I Atlas appears to exhibit controlled navigation and thermal management systems that suggest possible artificial origins. Its discovery has prompted emergency funding for enhanced observation campaigns and renewed debates about the potential for extraterrestrial reconnaissance missions monitoring our solar system. Atlas Telescope System. The ATLAS, Asteroid Terrestrial Impact Last Alert System, represents a revolution in automated sky surveys, comprising 4 strategically positioned telescopes across Hawaii, Chile, and South Africa. Originally designed to detect potentially hazardous near-Earth asteroids, the system has proven instrumental in discovering interstellar objects through its unprecedented sky coverage capabilities. Each telescope, though relatively modest at 0.5 meters in diameter, can scan the entire visible sky every 24 hours using sophisticated software algorithms that identify moving objects against the stellar background. ATLAS technology, developed by the University of Hawaii with NASA funding, played a crucial role in spotting 3I/Atlas and tracking its unpredictable motion patterns. The system's rapid cadence observations allow detection of extremely fast-moving objects that traditional surveys might miss during their less frequent scanning cycles. Automated detection algorithms flag anomalous objects for human review, enabling quick follow-up observations before interstellar visitors disappear beyond telescope range. ATLAS's success has paved the way for more frequent detections of cosmic wanderers, revolutionizing our understanding of how common these interstellar travelers might be and providing early warning for future scientific observation campaigns. Scientific theories and debates. The scientific community remains deeply divided over 3I/Atlas's true nature, with competing theories attempting to explain its anomalous properties. Some researchers favor the hydrogen iceberg hypothesis, proposing it represents a fragment of solid hydrogen from a distant stellar system, though this theory faces challenges regarding structural stability over interstellar timescales. Others suggest a nitrogen fragment similar to Pluto's surface material, potentially ejected during planetary formation in an alien solar system. Dr. Alan Fitzsimmons from Queen's University Belfast leads observations supporting natural origins, while University of Hawaii emphasizes the need for comprehensive spectroscopic data before drawing conclusions. The inconsistency between observed non-gravitational accelerations and minimal detectable outgassing continues to challenge traditional comet models. Exotic theories include the possibility of artificial construction, with some researchers noting the object's apparent thermal management capabilities and metallic composition. Statistical analysis suggests the probability of such a large object being discovered as only our third interstellar visitor approaches less than 0.1%, fueling debates about whether we're witnessing natural phenomena or something more extraordinary. These ongoing scientific debates highlight the need for enhanced observation capabilities and interdisciplinary approaches to understanding these cosmic mysteries. Future detection technology. The Vera C. Rubin Observatory, which began operations in Chile 2024, promises a revolution in detecting and studying celestial objects including interstellar visitors. Featuring an 8.4-meter primary mirror and the world's largest digital camera, this facility can capture images covering an area equivalent to 40 full moons in a single exposure. The observatory's legacy survey of space and time will photograph the entire southern sky every few nights for 10 years, creating an unprecedented movie of the dynamic universe. Expected to discover millions of new asteroids and potentially dozens of interstellar objects annually, the Rubin Observatory will provide statistical samples large enough to determine whether objects like 3I/Atlas represent rare anomalies or part of a larger population. Advanced machine learning algorithms will process the massive data streams in real time, identifying transient events and moving objects within hours of observation. The system's enhanced sensitivity and rapid cadence will enable detection of interstellar visitors when they're still far from the Sun, providing months or years of advance warning for detailed study campaigns. This technological revolution marks humanity's transition from serendipitous discovery to systematic interstellar object hunting. Theoretical implications. The discovery of objects like 3I/Atlas triggers profound theoretical implications for astrophysics, astrobiology, and humanity's understanding of our cosmic context. Statistical anomalies in these visitors' trajectories, sizes, and properties suggest either extraordinary coincidence or the existence of a broader population of interstellar objects that may include artificial constructs. SETI researchers are developing new frameworks for detecting extraterrestrial communications embedded in the behavior patterns of such objects, including analysis of acceleration profiles and thermal signatures that might indicate intelligent control. The concept of ancient probe networks has gained traction among theorists, proposing that advanced civilizations might deploy self-replicating surveillance systems throughout the galaxy to monitor emerging technological species. Dr. Michio Kaku and other theoretical physicists suggest these objects could represent first contact scenarios disguised as natural phenomena, allowing extraterrestrial intelligence to assess humanity's development without triggering societal disruption. Galactic archaeology models now incorporate the possibility of technological artifacts traveling between star systems, fundamentally altering our understanding of interstellar material exchange and the potential for cosmic civilizations to influence each other across vast distances and timescales through strategic deployment of monitoring technologies. Future endeavors. Looking ahead, ambitious space missions like the European Space Agency's Comet Interceptor aim to rendezvous with future interstellar visitors, potentially enabling close-up study and sample return from these cosmic wanderers. International collaboration between ground-based observatories and space-based telescopes is becoming increasingly coordinated to maximize scientific returns from rare interstellar encounters. NASA has proposed rapid-response spacecraft concepts that could be launched within months of detecting new visitors, using ion propulsion and gravitational assists to intercept objects before they exit our solar system. Project Lyra, a proposed mission to catch up with Oumuamua, demonstrates the technical feasibility of interstellar pursuit missions using current technology. This era marks humanity's transition from serendipitous discovery to purposeful exploration of interstellar space, setting the stage for our species' first direct encounters with materials from other star systems. Advanced spectroscopy, mass spectrometry, and imaging systems on future missions could provide definitive answers about the nature and origins of these visitors. Such endeavors may ultimately yield the first tangible proof of extraterrestrial intelligence or reveal exotic natural processes that expand our understanding of cosmic evolution and planetary formation throughout the galaxy. The ongoing journey of discovery surrounding interstellar objects like 3I/Atlas challenges us to rethink our place in the cosmos. As detection technology advances and observational capabilities improve, we may soon witness unprecedented revelations about our cosmic neighborhood and the possibility of extraterrestrial visitors. Whether these objects represent natural phenomena or something far more extraordinary, they've already begun transforming our understanding of the universe. The truth may be stranger than fiction. Stay tuned as we continue exploring these cosmic mysteries with future facts.
Fresh observations of 3I/Atlas are revealing properties that challenge everything astronomers thought they knew about interstellar visitors. While it was initially classified as a typical comet, new data suggests this object may be, deliberately concealing its true nature. Its perfect orbital alignment, suspicious timing, and anomalous behavior have sparked intense debates about whether we're witnessing natural phenomena or something far more extraordinary. The mounting evidence kind of forces us to confront an uncomfortable question. Could 3I/Atlas represent our second encounter with extraterrestrial technology disguised as a harmless space rock?
Fresh observations reveal mysteries.
Recent spectroscopic analysis of 3I/Atlas has uncovered anomalies that, honestly, defy conventional comet classification. Dr. Alan Fitzsimmons from Queen's University Belfast reported detecting unusual isotopic ratios in the object's outgassing that just don't match any known solar system materials. The object's infrared signature shows temperature variations that suggest internal heat sources, rather than simple solar warming. Most perplexing is the discovery of structured emissions, gas jets that appear to activate and deactivate in coordinated patterns rather than random sublimation. Dr. Michelle Bannister from the University of Canterbury noted that these emissions occur independently of the object's orientation toward the Sun, violating fundamental principles of cometary behavior. Radio telescope observations led by Dr. Avi Loeb detected low-frequency signals emanating from the object's vicinity, though their origin remains unexplained. The Hubble Space Telescope has captured images showing the object's surface reflectivity changes over time, suggesting either compositional variations or active surface modifications. These discoveries have transformed 3I Atlas from a routine interstellar visitor into one of the most enigmatic objects ever studied.
The scientific debate.
The astronomical community finds itself honestly deeply divided over 3I Atlas's true nature, with heated debates emerging at major conferences worldwide. Dr. Robert Warwick from the University of Hawaii, who discovered the object, maintains it represents a conventional ice-rich comet from another star system, arguing that all observed anomalies fall within the range of natural variation. However, an increasing number of researchers question this interpretation. Dr. Marco Micheli from the European Space Agency points to the object's non-gravitational accelerations that don't correlate with visible outgassing patterns. Dr. Daryl Seligman from the University of Chicago noted that traditional comet models fail to explain the object's persistent activity at distances where water ice should remain frozen. Dr. Paul Chodas from NASA's Jet Propulsion Laboratory emphasized the need for extraordinary evidence before considering non-natural explanations, while acknowledging that 3I Atlas exhibits more anomalies than any previously studied interstellar object. The debate reflects broader tensions in astronomy about how to approach phenomena that challenge established paradigms, with careers and reputations at stake.
The artificial origin hypothesis.
Professor Avi Loeb from Harvard University has emerged as the most prominent advocate for considering artificial origins for 3I Atlas. Building on his controversial interpretation of Oumuamua, Loeb argues that the object displays multiple signatures consistent with extraterrestrial technology. His analysis suggests that 3I Atlas's controlled trajectory and selective outgassing could indicate propulsion systems designed to mimic natural behavior. Dr. Loeb proposes that the object might represent a reconnaissance probe using stealth technology to avoid detection while studying our solar system. He notes that the object's arrival timing coincides with increased human space activity, potentially suggesting deliberate surveillance. Dr. Sarah Seeger from MIT supports considering artificial hypotheses, arguing that dismissing anomalous observations without investigation represents scientific bias. Critics like Dr. Alan Harris from the German Aerospace Center argue that Loeb's interpretations require multiple untestable assumptions, violating Occam's razor principles. The hypothesis has sparked public fascination while creating professional controversy within the astronomical community. Dr. Loeb maintains that science progresses by, challenging conventional wisdom, even when conclusions prove uncomfortable or unpopular.
Unusual detection pattern.
The circumstances surrounding 3I Atlas's discovery raise, troubling questions about detection bias and possible concealment. Dr. Larry Deneau from the Atlas survey system revealed that the object had been present in archived images for over 6 months before automated systems flagged it as anomalous. Trajectory reconstruction by Dr. Davide Farnochia shows that 3I Atlas entered our solar system in early 2024, remaining undetected despite passing relatively close to major asteroid surveys. Dr. Catalina Zuluaga from Harvard's Smithsonian Center for Astrophysics calculated that an object of 3I Atlas's size and brightness should have been detected months earlier by multiple survey systems. The late discovery becomes more suspicious when considering the object's approach vector. It arrived from a galactic direction with minimal stellar background, making it naturally difficult to detect against the sparse star field. Dr. Matthew Holman noted that this approach direction also corresponds to the galactic anti-center, where interstellar extinction is minimal, potentially indicating deliberate route planning. The detection pattern suggests either extraordinary coincidence or intentional concealment strategies.
Suspicious orbital characteristics.
Suspicious orbital characteristics. Statistical analysis of 3I Atlas's orbital parameters reveals improbable alignments that challenge natural origin theories. Dr. Fatih Namouni from Observatoire de la Côte d'Azur calculated that the object's near-perfect ecliptic plane alignment has only a 0.2% probability of occurring randomly for interstellar objects. More remarkably, 3I Atlas's trajectory creates close encounters with Venus, Mars, and Jupiter in a sequence that Dr. Kleomenis Tsiganis from Aristotle University determined has only a 0.005% probability of natural occurrence. The object's orbital inclination of just 1.3 degrees to the ecliptic means it travels through the most densely populated region of our solar system, maximizing potential gravitational interactions with planets. Dr. Alessandro Morbidelli noted that such alignments would be expected outcomes if the object were designed for systematic exploration of our planetary system. The timing of perihelion passage also coincides with optimal visibility from Earth, suggesting possible intentional revelation. These statistical anomalies compound the mystery surrounding 3I Atlas's true nature and purpose in our solar system.
The hidden approach strategy.
The timing of 3I Atlas's perihelion passage reveals what Dr. Avi Loeb describes as a cosmic blind spot strategy. Orbital mechanics calculations by Dr. Stephen Chesley from NASA JPL show that the object's closest solar approach occurs when Earth is positioned directly opposite in its orbit, creating a 7-month observation window with only 7% probability of natural occurrence. This positioning places the Sun between Earth and 3I Atlas during its most active phase, severely limiting ground-based observations and forcing reliance on space-based telescopes. Dr. Paul Wiegert from Western University noted that this configuration would be ideal for reconnaissance, allowing detailed study of Earth's orbital characteristics while minimizing detection risk. The object's outgassing pattern intensifies precisely when direct observation becomes difficult, potentially masking artificial activities behind natural phenomena. Dr. Loeb argues this represents sophisticated mission planning consistent with advanced intelligence. Critics counter that such interpretations reflect pattern recognition bias, but acknowledge the timing creates unprecedented observational challenges for determining the object's true nature.
Scientific opposition and evidence.
Mainstream astronomers have mounted vigorous opposition to artificial origin theories, citing fundamental physical and observational evidence. Dr. Olivier Hainaut from the European Southern Observatory argues that 3I Atlas's spectroscopic signature matches water ice sublimation, making artificial construction physically implausible. Size estimates derived from thermal infrared observations suggest the object measures 8 to 15 kilometers in diameter, far larger than any conceivable artificial probe. Dr. Bin Yang notes that constructing and propelling such a massive object would require energy resources exceeding the total output of entire stellar civilizations. Dr. Michael Ahearn's former colleague, Dr. Jessica Sunshine from the University of Maryland, emphasizes that all observed anomalous behaviors can be explained through exotic but natural processes involving pristine interstellar materials with unknown compositions. Dr. Alan Harris argues that selection bias influences interpretations. Humans naturally seek patterns and intelligence in random phenomena. However, artificial origin proponents counter that conventional explanations require increasingly improbable coincidences to account for the mounting statistical anomalies observed in 3I Atlas's behavior.
Ancient origins and anomalous behavior.
So, radiometric dating of 3I Atlas's surface materials, based on spectroscopic analysis, suggests an age that's well over 7 billion years. Meaning it actually predates the formation of our solar system. Dr. Dante Loretta from the University of Arizona pointed out that materials this old should, be heavily processed by cosmic ray bombardment. Yet 3I Atlas shows these really pristine surface characteristics. The object's proximity to the Sun, about 1.1 astronomical units, should produce a prominent comet tail. But high-resolution imaging by Dr. Hermann Bohnhardt from Max Planck Institute reveals only subtle outgassing, which is honestly inconsistent with typical water ice behavior. Then thermal modeling by Dr. Yanga Fernandez from the University of Central Florida shows that 3I/Atlas's internal temperature distribution just doesn't match what we'd expect from solid ice, suggesting either a hollow internal structure or maybe even exotic materials. On top of that, Dr. Michael Kelly from the University of Maryland found that the object's rotation period stays remarkably stable, despite active outgassing that should, in theory, create torques and rotational changes. These structural anomalies really challenge our natural formation models and, well, they might even suggest engineered stability mechanisms.
The stealth hypothesis.
There's something called the stealth hypothesis. Advanced civilizations might actually use dark forest strategies to avoid detection while conducting interstellar reconnaissance, according to Dr. Avi Loeb's, well, pretty controversial stealth hypothesis. This theory, which is inspired by Liu Cixin's science fiction concepts, suggests that technological civilizations stay hidden to avoid, potentially hostile encounters with superior species. Dr. Jacob Haq-Misra from the Blue Marble Space Institute argues that artificial objects disguised as natural phenomena would be, honestly, the optimal surveillance strategy, allowing for detailed planetary analysis without revealing any technological capabilities. Dr. Loeb proposes that 3I/Atlas's mimicry of comet behavior could actually represent sophisticated camouflage technology, designed to avoid triggering defensive responses from emerging civilizations. The object's strategic positioning and timing would enable a comprehensive assessment of human technological progress and space capabilities. Now, Dr. Seth Shostak from the SETI Institute remains skeptical, noting that real stealth would involve complete concealment, not just partial mimicry. However, Dr. Loeb counters that perfect concealment actually prevents data collection, so a controlled revelation becomes a necessary compromise for effective reconnaissance missions.
Lessons from Oumuamua.
The 2017 Oumuamua encounter really serves as a cautionary tale about missed opportunities and, scientific conservatism. Dr. Robert Warwick, who actually discovered both objects, admits that Oumuamua's anomalous properties just weren't investigated enough, mostly due to limited observation time and, technological constraints. Dr. Abraham Loeb argues that the astronomical establishment's quick dismissal of artificial origin hypotheses for Oumuamua represents scientific bias, not rigorous analysis. 3I/Atlas gives us a second chance to properly investigate anomalous interstellar visitors, this time with better instruments and longer observation periods. Dr. Michelle Bannister emphasizes, the importance of systematic data collection instead of jumping to predetermined conclusions, and points out that both natural and artificial explanations deserve equal scientific scrutiny. Dr. Sarah Seeger from MIT argues that dismissing extraordinary possibilities without investigation actually violates fundamental scientific principles. The lesson from Oumuamua is pretty clear. Anomalous visitors require comprehensive investigation, not just reflexive categorization. Dr. Loeb maintains that future discoveries will vindicate careful analysis of seemingly impossible phenomena, regardless of what the ultimate explanation turns out to be. 3I/Atlas continues to challenge our understanding of what travels between the stars, whether it represents some exotic natural phenomena or, something far more extraordinary. This object has really forced astronomers to confront the possibility that we may not be alone. The mounting statistical anomalies and honestly suspicious behaviors demand serious scientific investigation rather than just reflexive dismissal. As 3I/Atlas races toward its closest solar approach, we've got a limited window to unlock its secrets. Could this be our second encounter with extraterrestrial technology? Share your thoughts below, and if this cosmic mystery intrigued you, hit like, share with fellow space enthusiasts, and subscribe to Future Facts for more incredible discoveries. In the vast expanse beyond our solar system, the realm of interstellar space challenges our understanding of the cosmos. From the familiar faces of planets like Earth, Mars, and Jupiter, humans have long dreamed of what lies beyond. The heliopause, the boundary where solar influence ends, marks the start of true interstellar space. Since Voyager 1 crossed this threshold in 2012, revealing complex magnetic and plasma phenomena, astronomers have tracked enigmatic visitors like Oumuamua in 2017 and Borisov in 2019. Now comes the mysterious visitor, 3I/Atlas, promising to deepen our cosmic perspective.
Beyond the heliopause, our interstellar visitors.
Beyond the heliopause lies a vast territory filled with rarefied plasma, cosmic dust, and magnetic fields shaped by the galaxy. The solar wind's protective bubble ends at roughly 121 astronomical units, where Voyager 1 provided unprecedented data on the transitions between solar and galactic environments. This region, once thought to be sterile, teems with dynamic phenomena including plasma waves, magnetic reconnection events, and cosmic ray interactions that alter our view of cosmic landscapes. Dr. Ed Stone, Voyager's project scientist, noted that crossing into interstellar space revealed an environment far more complex than anticipated. Interstellar visitors like Oumuamua and Borisov offer rare glimpses into this frontier, acting as natural probes from distant star systems to ours. These objects carry information about stellar formation processes, planetary system evolution, and galactic chemical composition that would otherwise remain inaccessible. Their study has revolutionized our understanding of material exchange between star systems, revealing the dynamic nature of our galactic neighborhood.
The third visitor, 3I/Atlas discovery.
3I/Atlas was first detected by the Asteroid Terrestrial Impact Last Alert System in early 2025, marking a historic moment as humanity's third confirmed interstellar visitor. Astronomers worldwide scrambled to confirm its hyperbolic trajectory, ensuring it was genuinely from beyond our solar system rather than a long-period comet. Its approach from the constellation Lynx at extraordinary velocities immediately marked 3I/Atlas as a unique opportunity for scientific study. Dr. Robert Warwick from the University of Hawaii, who also discovered Oumuamua, led early observations confirming its strange orbital parameters and unusual characteristics. Unlike its predecessors, 3I/Atlas displayed continuous cometary activity and potentially larger size, intriguing scientists worldwide who aimed to unlock its secrets before it disappeared forever. Initial spectroscopic observations revealed complex chemical signatures suggesting a composition unlike typical solar system comets. The discovery triggered an international observation campaign involving major telescopes across 6 continents, demonstrating the global cooperation essential for studying these rare cosmic visitors.
A hyperbolic journey at 58 km.
The Atlas survey system, employing wide-field telescopes in Hawaii and Chile, represents cutting-edge technology designed to detect potentially hazardous near-Earth objects. Its success in capturing 3I/Atlas demonstrates how advanced algorithms optimized for fast-moving objects can identify interstellar visitors among millions of routine asteroid observations. Dr. Larry Deneau, who leads the Atlas project, explained that the system's 4-telescope network scans the entire visible sky multiple times each night, creating a comprehensive catalog of moving objects. The detection of 3I/Atlas required sophisticated orbit determination software capable of distinguishing hyperbolic trajectories from elliptical ones. Atlas's rapid response capabilities provided crucial early warning, enabling astronomers to begin intensive observations months before the object's closest solar approach. The system's real-time processing algorithms automatically flagged 3I/Atlas as anomalous based on its velocity vector and trajectory characteristics. This breakthrough exemplifies how technological evolution enables rapid response and detailed tracking of transient cosmic visitors, expanding humanity's reach into the unknown.
From A11PL3Z to C2025N1, the naming journey.
The naming journey follows established astronomical protocols. When the object was first detected, it got the provisional designation A11PL3Z, which marks it as an asteroid-like object discovered in the second half of 2025. After astronomers confirmed its cometary activity through spectroscopic analysis, it was reclassified as C/2025N1, which means it's a comet discovered in July of 2025. The International Astronomical Union then assigned the official prefix 3I/, marking it as the third confirmed interstellar object after Oumuamua, 1I/, and Borisov, 2I/. The name Atlas honors the Discovery Survey System, following IAU traditions of crediting the discovering institution. Dr. Gareth Williams, director of the Minor Planet Center, oversaw the naming process, which really balances the need for rapid identification with conventions that reflect astronomical heritage. The provisional to permanent designation pipeline usually takes several months, as astronomers need enough observational data to confirm orbital characteristics. This systematic approach helps prevent misclassification and make sure proper credit is given. The naming process also reflects international cooperation in astronomy, since discoveries made by one team benefit the whole scientific community. Committee guidelines are in place to ensure that names remain scientifically appropriate, while honoring significant contributions to astronomical discovery.
Brightness, rotation, and the 29-hour cycle.
3I/Atlas follows a hyperbolic orbit, traveling at about 58 kilometers per second relative to the Sun, which means it's on a one-way trip that will never return to our solar system. Its path cuts through the ecliptic plane with impressive precision, bringing it within gravitational reach of major planets like Mars, Venus, and Earth. Orbital calculations by Dr. David Farnokia at NASA's Jet Propulsion Laboratory show that this object's path creates several planetary encounters, which will slightly tweak its trajectory through gravitational assists. The perihelion passage on October 30, 2025, is the best time to observe it, as it comes within 1.2 astronomical units from the Sun. Scientists like Dr. Alan Fitzsimmons are looking at how these gravity-influenced changes in trajectory can teach us about interstellar dynamics and how planetary systems interact. The approach geometry actually allows observations from both hemispheres as it moves from the southern to the northern skies. Computer simulations predict that these gravitational encounters will speed up 3I/Atlas by a few kilometers per second, showing how our solar system can act like a gravitational slingshot for interstellar objects.
Coma tail and cometary activity.
Observational campaigns show that 3I/Atlas measures somewhere between 8 and 15 kilometers in diameter, making it quite a bit larger than Oumuamua, but about the same size as Comet Borisov. Light curve analysis by Dr. Karen Meach at the University of Hawaii suggests a rotation period of around 29 hours, which might mean it's a slow rotator, or maybe even has a complex tumbling motion. The object's brightness variation suggests it's not a perfect sphere, maybe elongated like Oumuamua but not as extreme. Unlike most comets, 3I/Atlas has a persistent but faint coma, and doesn't develop a pronounced tail, even as it gets closer to the Sun. Spectroscopic studies led by Dr. Bin Yang from the European Southern Observatory have found complex mixtures of water ice, carbon monoxide, and organic compounds in its makeup. Its unusual reflectivity patterns hint at surface materials that are different from typical solar system comets, possibly pointing to its formation in a completely different stellar environment. Thermal modeling shows that 3I/Atlas holds onto internal volatiles that start to sublimate at greater distances than we'd expect, which is what creates its unique cometary activity.
Oumuamua versus Borisov versus 3E Atlas.
Comparing these three confirmed interstellar visitors, we see, honestly, just remarkable diversity in the cosmic debris traveling between star systems. Oumuamua, which was discovered by Dr. Robert Warwick back in 2017, still remains an enigma with its extreme cigar-like shape, and that unexplained non-gravitational acceleration that, well, defied conventional comet behavior. Comet Borisov, found by amateur astronomer Gennady Borisov in 2019, actually behaved like a typical comet, with visible coma development, active outgassing, and familiar spectroscopic signatures. Now 3I/Atlas kind of occupies the middle ground, displaying characteristics that bridge both previous visitors, while also introducing entirely new complexities. Dr. Olivier Haynaut notes that 3I/Atlas shows controlled outgassing patterns and variable brightness that, frankly, just don't match traditional comet models. Statistical analysis by Dr. Alan Harris suggests these three objects represent different formation environments and evolutionary histories. Oumuamua's rocky composition contrasts sharply with Borisov's ice-rich nature and 3I/Atlas's hybrid characteristics. The growing sample indicates that interstellar space contains diverse populations of objects ejected from planetary systems during their formation phases. And Dr. Michelle Bannister emphasizes that only through multiple observations can patterns emerge, revealing the vast variety of interstellar debris shaping galactic material exchange.
A 311 billion-year-old traveler.
Radiometric dating techniques applied to spectroscopic data suggest that 3I/Atlas could be anywhere from 3 to 11 billion years old, potentially